The Principles Underlying Radio Communication, 2nd edition, Radio Communication Pamphlet Number 40, prepared by the Bureau of Standards, revised to May 24, 1921, Signal Corps, U.S. Army. 1922. War Department, Document Number 1069, Office of the Adjutant General. War Department, Washington, June 10, 1921. The following publication entitled The Principles Underlying Radio Communication is published for the information and guidance of all concerned. By order of the Secretary of War, Peyton C. March, Major General, Chief of Staff. Official, P.C. Harris, the Adjutant General. Introduction. What radio communication means. In military service, all possible means of communication are used, including the most primitive. Some of the earliest methods were by means of beacon fires and much later flags. However, the best and most rapid are the electrical methods. These include the ordinary wire telegraph and telephone and the wireless or radio apparatus. Without wire connecting lines, radio messages are sent from one point to another on the battlefront, from ship to shore, across the oceans, to airplanes, and even to submerged submarines. Business and social life have been profoundly modified by the advent of electric communication, and recent developments in radio have done much to make communication easy between distant points. When a pebble is thrown into the smooth water of a pond, it starts a series of circular ripples or waves, which spread out indefinitely with the speed of a few hundredths of a meter per second. See the frontispiece. Similarly, an electric disturbance starts electric waves, which spread out in all directions and travel with the velocity of light, which is 300 million meters per second, or about 186,300 miles per second. It is by means of these electric waves that radio messages are sent. In order to make use of electric waves for the practical purpose of sending messages, it is necessary, A, to produce regular electric disturbances in a circuit which starts the waves. These disturbances are electric currents which reverse rapidly in direction. B, to get the waves out into surrounding space through which they travel with great speed. This is done by means of transmitting antenna. C, by means of these waves to set up electric currents in a receiving circuit at the distant station. The device which these waves strike as they come in, and which turns them over to the receiving circuit, is called the receiving antenna. D, to change these currents so that they may be detected by electric instruments. The operator usually receives the message through signals in a telephone receiver. In communication by flags, messages are transmitted by a code, in which each letter of the alphabet is represented by a position or combination of positions of flags. In communication by radio telegraphy, a code is used consisting of combinations of very short signals or dots, and longer signals or dashes. In communication by radio telephony, the voice itself is transmitted and no code is necessary. The student of radio communication needs a more thorough knowledge of electrical theory than that needed for some branches of electrical work. This fact needs emphasis for the beginner. Of course, a man can learn to operate and care for apparatus without having a real understanding of its underlying principles. It only requires that he have a certain type of memory, industry, and a little common sense. But a man with only this kind of knowledge of his subject is of limited usefulness and resourcefulness, and cannot advance very far. The real radio man must have some training in the whole subject of electricity and magnetism, as well as rather intimate familiarity with some restricted parts of it. An understanding of radio communication requires some knowledge of the following subjects. A, direct and alternating currents and dynamo machinery. B, high-frequency alternating currents including the subject of condenser discharge. C. Conduction of electric current in a vacuum as well as in wires. D. Electric waves which involve some acquaintance with modern ideas of electricity and the ether. E. The apparatus used for the production and reception of electrical waves. Two. Fundamental ideas of the electric circuit. It is common knowledge that a battery supplies what is known as a current of electricity. To obtain the current, there must be a complete closed conducting path from the battery through the apparatus, which is to be acted on by the current and back again to the battery. For example, when connecting up an electric bell, a wire is carried from one binding post of the battery to one of the binding posts of the bell, and a second wire is brought from the other binding post of the bell back to the remaining binding post of the battery. Any break in the wire immediately causes the current to stop and the bell to be silent. This furnishes an easy method of controlling the ringing of the bell, since it is only necessary to break the circuit at one point to stop the current, or to connect across the gap with a piece of metal to start the current going again. Thus the battery supplies the power to operate the bell, and the button opens and closes the circuit and thus controls the delivery of that power to the bell. Similar consideration may apply when using the city lighting circuit. Wires from the generator at the central station are brought to the lamp, motor, or heating device to be supplied, and the flow of current to this device controlled by means of a switch. The switch consists of pieces of metal which may be brought into contact when desired. The operation of the switch makes or breaks the contact. One handle may control two switches so that with one motion the circuit can be broken at two places. The switch may be located on the wall in any one of the number of different forms such as snap switch, the push button switch, and the knife switch. The switch may be located in the socket which holds the lamp. Such a socket is called a key socket. It makes no difference at which part of the circuit the current is interrupted. The flow of current will stop whether the break is made at the lamp or in one wire at some distance from the lamp, or by opening a switch at the switchboard at the central station. Electricity must then be regarded as flowing in every part of the circuit, so that electricity is leaving the battery or dynamo at one side and going back to it at the other side. Current. The current flowing in a circuit is no stronger at one point of the circuit than at another. This can be proved by connecting a measuring instrument called an ammeter into the circuit at different points, A, B, or C. Figure 2. It is found to register the same at whatever point this test is made. A useful illustration of the electric circuit is a closed circuit of pipe, completely filled with water and provided with a pump, P, or some other device for causing the water to circulate. The amount of water which leaves a given point in each second is just the same as the amount which arrives in the same length of time. Now, in the electric circuit, we have no material fluid, but we suppose that there exists a substance which we call electricity. Electricity behaves in the circuit much like an incompressible fluid in a pipeline. We are very sure that electricity is not like any material substance which we know, but the common practice among students and shopmen of calling it juice shows you that they think of it as like a fluid. We will, then, imagine the electric current to be a stream of electricity flowing around the circuit. One way of measuring the rapidity with which water is flowing is to let it pass through a meter which registers the total number of quarts or gallons which pass through. By dividing the quantity by the time it has taken to pass, we obtain the rapidity of flow. There are instruments by means of which it is possible to measure the total quantity of electricity which passes any point in the current during a certain time. If we divide this quantity by the time, we obtain the amount of electricity which has passed in 1 second. This is a measure of the current strength. In practical work, however, the strength of the current is measured by instruments and meters. which show at each moment just how strong the current is, in somewhat the same manner as we may estimate the swiftness of a stream by watching a chip on the surface. This kind of an instrument enables us to tell at a glance what the current is, without the necessity for a long experiment, and further, we may detect changes in the strength of the current from moment to moment. In this connection, it will be remembered that two measuring instruments are to be found on an automobile. The speedometer shows what the speed of the car is at each moment, so that the driver may know instantaneously whether he is exceeding the speed limit and govern himself as he sees fit. The other instrument shows how many miles have been covered on the trip, and of course the average speed may be calculated from its indications, if the length of the trip has been timed. The instrument for measuring total quantity of electricity corresponds to the recorder of the total miles traversed. The ammeter corresponds to the speedometer. Electromotive force. The water will not flow in the pipeline, Figure 3, unless there is some force pushing it along, as for example a pump, and it cannot be kept flowing without continuing pressure. Electricity will not flow in a circuit unless there is a battery or other source of electricity in the circuit. The battery is for the purpose of providing an electric pressure. To this is given the name electromotive force, that is, a force which moves the electricity. This is usually abbreviated to EMF. The larger the number of cells which are joined in the circuit in such a way that their pressures will add, the greater the electric pressure in the circuit and the larger the current produced, just as the rapidity of the flow of the water in the pipeline may be increased by increasing the pump pressure. Resistance. There is always some friction in pipe, whatever its size or material, and this hinders the flow of the water to some extent. If it were not for the friction, the water would increase indefinitely in speed. Similarly, there is friction in the electric circuit. This is called the resistance of the circuit. The greater the resistance, the smaller the current which can be produced in the circuit by a given battery, just as the greater the friction, the less rapid the flow of water with a given pump acting. A resistance coil at any point in the circuit corresponds to a partially closed valve in the pipe at any point. Steady and variable currents. If a pipe is connected to a large reservoir of water maintained at the same level, the steady pressure of the constant head of water will cause a steady flow of water in the pipe. The quantity of water which will pass a given point in 1 second will be the same at all times. Certain sources of electricity, such as batteries and some kinds of dynamos, produce an electromotive force which is practically constant, and will cause a practically constant current to flow in circuits to which they are connected. A steady electric current in one direction is called a direct current. In the case of ordinary force pump, the water is given a succession of pushes all in the same direction, but separated by intervals when the water is not being pushed. The heart is such a pump which applies successive impulses to the blood and causes it to circulate. A pipe supplied by a force pump is usually discharging some water all the time, but successive spurts occur when an unusually large stream of water is discharged for a moment. The frequency of these spurts corresponding to the rate at which the pump is being run. Similarly, there are sources of electromotive force which act intermittently. When such an electromotive force is connected to a circuit, the current flows always in the same direction but varies in magnitude from instant to instant. A current of this kind, which pulsates regularly in magnitude, is called a pulsating current. A very important kind of current for radio work is that known as alternating current. This is analogous to the kind of flow which would be produced if, instead of being acted on by a pump, the water were agitated by a paddle which moved back and forth rapidly over a short distance, without traveling beyond certain limits. Under this impetus, the water no sooner gets up speed in one direction than it is compelled to slow up and then gather speed in the opposite direction. and so on over and over again. The water simply surges first in one direction and then in the other, so that a small object suspended in the water would not travel continuously around the pipeline, but would simply oscillate back and forth over short distance. Effect of a condenser. As a further case, let us suppose that an elastic partition, E, is arranged in the pipe, so that no water can flow through or around it. If pump P or a piston acts steadily, the water moves a short distance until the partition is stretched enough to exert a back pressure on the water equal to the pressure of the pump, and then the movement of the water as a whole ceases. If, on the contrary, a reciprocating motion is given to the water by P, the water moves back and forth, stretching the partition first in one direction and then in the other, and the water surges back and forth between short limits which are determined by the elasticity of the partition. We have in this case an alternating current of water in spite of the presence of the partition. An electric condenser acts just like an elastic partition in a circuit. No direct current can flow through it, but an alternating current of an amount depending on the nature of the condenser can flow when an alternating EMF acts on the current. As an extreme case, we may imagine the pipeline replaced by a long tube filled with water and the ends closed by elastic walls. Suppose an alternating pressure to be given to the water in the tube, or even let the tube be tipped first in one direction and in the other. The water will oscillate back and forth a short distance in the tube, first stretching the wall at one end and then the wall at the other. Small alternating flow is thus set up, although there is not a complete circuit for the water to flow through. Analogous to this case is that of the electrical oscillation in an antenna. Such a flow of electricity without a complete conducting circuit is called a displacement current. It is always necessary, in order to produce a displacement current, that the circuit shall have electrical elasticity somewhere. That is, an electric condenser shall be present. The importance of the electric current lies in the fact that it is an energy current. A current of water transports energy, so does a current of air. It is the motion that counts, and to utilize the energy of motion, we must do something tending to stop the motion. In the case of water flowing in a channel, we may do this by causing the water to flow under a water wheel whose resistance to turning causes it to absorb energy from the current of water. Any material substance, by virtue of its mass, can be made to act as a vehicle for transporting energy from one place to another, providing only it is set into motion. In the case of the electric current, we do not need to inquire whether electricity has mass. We are concerned in the use of electrical apparatus with the transformation of the energy of the current into other familiar forms of energy: heat, light, and motion. The electric current is the vehicle by which we transmit energy from the central station to the consumer, and we are not, for practical purposes, concerned with the method of carrying the energy, any more than we need to inquire into the nature of the belt by which mechanical energy is carried from one wheel to another, or into the chemical nature of the water which is furnishing the power in a hydraulic plant. The electric current itself cannot be seen, felt, smelt, heard, or tasted. Its presence can be detected only by its effects, that is, by what happens when it gives up some of its energy. Thus, an electric current may give up some of its energy and cause a motor to turn. Electrical energy has been given up and mechanical energy takes its place. Similarly, electric energy may disappear and heat or light may appear in its place, or a chemical effect may arise. When a person feels an electric shock, it is not the current itself he feels, but the muscular contractions and other physiological effects caused by the passage of the current. The electric lamp has an effect on the eye. We do not, however, see the electric current in the lamp, but the effect on the eye is due to the light waves sent off by the hot filament. The energy of the current has been changed over into heat in the lamp. When we hear a sound in the telephone receiver, it is not the electric current we hear, but merely the vibration of the thin diaphragm. The electric current has used some of its energy in causing the diaphragm to vibrate. The acid taste noticed when the tongue is placed across the poles of a dry battery is due to the chemical decomposition of the saliva into the other compounds as a result of the passage of the current through it. In the next section, the electric current is studied through the effects it produces, and in the later sections, it is given a more exact and detailed treatment. Chapter 1, Elementary Electricity. A. Electric current. 3. Effects of electric current. Most of the applications of electricity depend upon the movement of electricity, that is, the electric current. The effects of stationary electricity, electric charge or quantity of electricity, are of importance in connection with such subjects such as electric condensers, and in the study of electrons, but it is moving electricity or current flow that is of greatest practical importance. A wire in which an electric current is flowing usually looks exactly like a wire without current. Our senses are not directly impressed by the phenomena of electricity, and hence it is necessary to depend upon certain effects which are associated with the flow of current through a conductor when it is desired to determine whether or not a current exists. Some of these effects are as follows. A. If a straight wire carrying an electric current is brought near a small magnet, such as a compass needle, which is so placed that the axis about which it turns is parallel to the axis of the wire, then the needle is deflected a certain amount and tends to become tangent to a circle about the wire. It then remains in the new position as long as the current does not vary. B. A wire with a current passing through it will be at higher temperatures than the same wire before the current flows. If the wire is large or the current is small, this can be detected only by a sensitive thermometer. But under some conditions, as in ordinary incandescent lamp, the rise of temperature is so great as to cause the wire to glow. C. If the wire through which the current is flowing is cut, and if the separated ends are immersed in a solution in water of any one of a wide variety of substances, there will be a chemical change in the solution. This chemical change may become apparent by a change in the color of solution, by a deposit on one of the wires, or otherwise, and gas may be evolved. Thus, if the solution is copper sulfate, copper will be deposited. The attention of the student should be fixed upon these effects of the current rather than upon the current itself. It is in terms of these effects that electric currents are detected, measured, and applied. Thus, the magnetic effect is the basis of dynamo-electric machinery and radio communication. The heating effect, B, makes possible electric cooking and electric lighting, and the chemical effect, C, makes possible electroplating, electric batteries, and various chemical processes. All three effects are utilized in making electric measurements. It must be kept in mind that such expressions as flow and current, and many other electrical terms, are merely survivors from an earlier day when electricity was supposed to be a fluid which actually flowed. Such terms are, however, helpful in forming mental pictures of the real phenomena of electricity. Attention must always be centered on the facts and effects which these terms represent, and the words or phrases themselves must not be taken literally. 4. Direction of current. By means of the magnetic effect, it is readily shown that electric current has direction. If the wire in Fig. 7 be withdrawn from the plate O, and reinserted in the opposite direction, the compass needle will indicate a direction nearly opposite to that of the original position. The same result is secured if the wire is left unchanged and the connections to the terminals of the battery are reversed. The direction of flow of electric current is a matter of arbitrary definition, and in practice the student will usually determine the direction by means of an instrument with its terminals marked positive and negative. It is assumed that current enters the instrument at the positive terminal and leaves it at the negative terminal. The magnetic effect may also be used in specifying the direction of the current. See section 40, page 103. Again, referring to figure 7, it is seen that as the current flows down through the plane, the compass needle at every point in the plane tends to set itself tangent to one of the concentric circles about the wire. As the observer looks along the conductor in the direction in which the current is flowing, the north-seeking or north-pointing pole of the needle will point in a clockwise direction around the conductor. That is, it will point in the direction it would assume if following the advancing hand of a clock having the conductor as a pinion. Other useful rules for remembering the same relative directions are as follows. A. Grasp the wire with the right hand and with the thumb extended along the wire in the direction of the current. The curved fingertips will then indicate the direction of the magnetic effect. B. Imagine an ordinary right-hand wood screw being advanced into a block in the direction in which the current is flowing. The direction in which the screw rotates then indicates the direction of the magnetic field around the wire or conductor as it would be indicated by a compass needle. The student should assure himself of complete familiarity with one of these rules by considerable practice with a small compass and a simple electric circuit. For the extension of this relation, determine the polarity of a helical coil carrying a current. See section 42, page 105. 5. Measurement of electric current and quality of electricity. All three of the simple ways by which electric current may be detected provide means of current measurement. The magnetic effect of the current may be used by mounting a wire and a magnet in such positions that when a current flows in the wire, either the magnet or the wire moves. The heating effect of the current is utilized in hot wire instruments, where the increase in length of the heated wire is utilized to move a pointer over a dial. These principles are used in a great variety of instruments for the measurement of current. The amount of current is read from the scale or dial of the instrument. The scale is usually graduated at the time when the instrument is standardized in a unit called the ampere. The instruments are called ammeters. The ampere is a unit of magnitude of which has been defined by international agreement. In its definition, the third effect of the electric current described above is made use of. The mass of a metal which is deposited out of a solution by an electric current depends on the product of the strength of the current by the time it is allowed to flow. Thus, a certain current flowing for 100 seconds is found, experimentally, to be able to deposit as much of a metal as a current 100 times as great passing for 1 second, etc. Remembering that the strength of the current is the rapidity of flow of electricity, it is evident that the product of strength of current by time of flow gives the total quantity of electricity which has passed. The mass of a metal deposited by the current is then proportional to the total quantity of electricity which has flowed through the solution. Equal quantities of electricity will deposit different masses of different metals, but the mass of any chosen metal is always the same for the same quantity of electricity. The ampere, properly called the international ampere, is that unvarying current which, when passed through a neutral solution of silver nitrate, will deposit silver at the rate of 0.001118 gram per second. A convenient way of remembering this figure is that it is made up of 1.2 noughts, 3 ones, and 4 twos. 8. While current could be regularly measured by the process used in establishing this unit, this is not done in actual practice. The measuring instruments used in actual measurements are, however, standardized more or less directly in terms of the unit thus defined. Quantity of electricity is usually measured in a unit called the coulomb. The coulomb is the quantity of electricity transferred by a current of 1 ampere in 1 second. Another unit sometimes used for measuring quantity of electricity is the ampere hour, which is the quantity of electricity transferred by a current of 1 ampere in 1 hour, and is therefore equal to 3,600 coulombs. Section 6. Electrons. When electric current flows in a conductor, there is a flow of extremely small particles of electricity called electrons. The study of these particles is important not only in connection with current flow, but also in light and heat and chemistry. The reason for this is that all matter contains them. Matter of all kinds is made up of atoms, which are extremely small portions of matter. A drop of water contains billions of them. The atoms contain electrons, which consist of negative electricity. The electrons are all alike, and are in turn much smaller than the atoms. Besides containing electrons, each atom also contains a certain amount of positive electricity. Normally, the positive and negative electricity are just equal. However, some of the electrons are not held so firmly to the atom, but what they can escape when the atom is violently jarred. When an electron leaves an atom, there is less negative electricity than positive in the atom. In this condition, the atom is said to be positively charged. When, on the other hand, an atom takes on one or more extra electrons, it is said to be negatively charged. The atoms in the matter are constantly in motion, and when they strike against one another, an electron is sometimes removed from an atom. This electron then moves about freely between the atoms. Heat has an effect upon this process. The higher the temperatures, the faster the atoms move and more electrons given off. If a hot body is placed in a vacuum, the electrons thus given off travel from the hot body out into the surrounding space. This sort of motion of electrons is made use of in the electron tube, which is the subject of Chapter 6 of this book. The motion of the electrons inside a wire or other conductor is the basis of electric current flow. This is discussed with the various important properties of electrons in a book by R.A. Millikan, The Electron, and briefly in Radio Instruments and Measurements, circular number 74 of the Bureau of Standards, page 8. This circular is sometimes referred to as C74. B. Resistance and resistivity. Section 7. Resistance and conductance. The flow of current through a circuit is opposed by a property of the circuit called its resistance. The resistance is determined by the kinds of materials of which the circuit is made up, and also by the form, length, and cross-section of various portions of the circuit. Provided that the temperature is constant, the resistance is constant, not varying with the current flowing through the circuit. This important relation is called Ohm's law and will be discussed further in section 14. All substances may be grouped according to their ability to conduct electricity, and those through which current passes readily are called conducting materials or conductors, while those through which current passes with difficulty are called insulating materials or non-conductors. However, there is no known substance which admits current without any opposition whatever, nor is there any known substance through which some small current cannot be made to pass. There is no sharp distinction between the groups as they merge gradually one into the other. Nevertheless, it should be kept in mind that conductors have a conducting power which is enormously greater than the conducting power of an insulator. The minute current which can be forced through an insulator under certain circumstances is aptly called a leakage current. An ideal insulator would be one which would allow absolutely no current to flow. Examples of good conducting materials are the metals and that class of liquid conductors called electrolytes. Examples of insulating materials are dry gases, glass, porcelain, hard rubber, and various waxes, resins, and oils. A circuit which offers but little resistance to a current is said to have good conductance. Representing this by G, we may write G equals 1 over R, or R equals 1 over G. For example, a circuit having a resistance of 10 ohms will have a conductance of 0.1, and one of 0.01 ohm will have a conductance of 100. The unit of resistance, called the ohm, is defined in terms of a standard consisting of pure mercury of accurately specified length, mass, and temperature. The international ohm is the resistance offered to the flow of an unvarying current by a column of mercury 106.3 centimeters high and weighing 14.4521 grams at a temperature of 0 degrees Celsius. For very small resistances, the millionth part of an ohm is used as a unit and is called the microohm. For high resistances, a million ohms is used as a unit and is called the megaohm. The opposition to flow of a current referred to above is analogous to friction between moving water and the inner surface of the pipe through which it flows. It is always accompanied by the production of heat. If an unvarying current is maintained through a conductor, this production of heat is at a constant rate. The total heat produced in T seconds is found to be proportional to the resistance of the current circuit, to the square of the current, and to the time. Thus, W equals R I squared T. From this it follows that R for a given portion of the circuit might be measured by the heat generated in that portion. The heat will be measured in joules, when the current is in amperes and the resistance in ohms, and the time in seconds. To find the heat in calories, the relation W divided by J equals H will be used, where W is in joules and J, 4.18, is the number of joules in 1 calorie. The relation given in equation 2 is sometimes called Joule's law. And that equation is W equals RI squared T. Section 8. Resistivity and conductivity. For a given piece of wire of uniform cross-section, its resistance is found to be proportional directly to its length and inversely to its cross-sectional area. In addition, the resistance depends upon the kind of material of which the wire is composed. These relations may be expressed by the following equation. R equals P times L over S, where R is the measured resistance of the sample, L is the length, S is its cross-section, and P is a constant, characteristic of the given material. Solving this equation for P, we have P equals R times S over L. If a piece of material is chosen having unit cross-section and unit length, it is seen that P is equal to the resistance of the piece measured between opposite faces. The factor P is called the resistivity or specific resistance of the substance and is defined as the resistance between opposite faces of the unit cube. The ohm or the microohm is commonly used as the unit of resistance and the centimeter as the unit of length. Instead of expressing resistivity in these units, it may also be given in terms of ohms per foot of wire 1 mil, 0.001 inch in diameter, or in ohms per meter of wire 1 millimeter in diameter. Another group of resistivity units is based upon the mass of sample instead of its volume. For example, A. Resistance of a uniform piece of wire of 1 meter length and 1 gram mass, or B. The resistance of a wire of 1 mile length and of 1 pound mass. Practically, for some purposes, mass resistivity is preferable to the volume resistivity for the following reasons. A. Sufficiently accurate measurements of cross-section of specimens are frequently difficult, or for some shapes, impossible. B. Material for conductors is usually sold by weight rather than volume, and hence the data of greatest value are most directly given. The mass units and volume units are readily interconverted, provided that the density of the material is known. If in the equation we substitute for S the value of V over L, where V is the volume, and for V its equivalent M over D, where M is the mass and D is the density, we have R equals P times D times L squared over M. The quantity PD is called the mass resistivity of the material. The volume resistivity may then be transformed into mass resistivity, or vice versa, taking care that all quantities are given in constant units. As examples of resistance, the following will be useful. 1. 1 ohm is the resistance of about 157 feet of number 18 copper wire with a diameter about 1 millimeter or 40 mils or 0.04 inch. 2. 1,000 feet of number 10 iron wire has a resistance of about 6.5 ohms. Tables of resistivity for various materials are given in Table 21, Circular 74 of the Bureau of Standards. Just as conductance is the reciprocal of resistance when considering the properties of a circuit as a whole, so conductivity is the reciprocal of resistivity when considering the properties of a given material. Its unit is the mho, or reciprocal ohm. Section 9. Temperature coefficient. The electrical resistance of all substances is found to change more or less with any change in temperature. All pure metals and most of the metallic alloys show an increased resistance with rising temperature. Carbon and most liquid conductors, like battery solutions, show a decrease in resistance as the temperature increases. Experiment shows that the resistance at a temperature T can be calculated if the resistance at zero temperature, melting point of ice, has been measured. The formula is RT equals RO plus RO alpha O T, where RO is the resistance of the sample at zero, and alpha O is the change in 1 ohm when the temperature changes from 0 to 1 degree Celsius. The factor alpha O is called the temperature coefficient of the resistance for the material. Solving equation 6 for alpha O, we have alpha O equals RT minus RO over RO T. Equation 7 shows alpha O is the value of the change in the resistance per ohm degree change in temperature, or it is the fractional change of the total resistance for 1 degree change in temperature. If the resistance of the material decreases with a rise in temperature, then the temperature coefficient is negative. If a reference temperature T1 is chosen, which is not 0, Then the resistance R2 at some other temperature T2, which is higher than T1, may be found from the resistance R1 at T1 by following equation. R2 equals R1 bracket 1 plus alpha 1 parentheses T minus T1 in parentheses end bracket. Equation 8, where alpha 1 is the temperature coefficient for the reference temperature T1. Calculations of this sort are simplified by the use of a table of values of alpha for various initial reference temperatures. See Table 21, Circular 74. Section 10, Current Control. In electrical work, the need is constantly arising for adjusting a current to a specified value. This is usually done by varying the resistance of the circuit. Changes in the resistance of a circuit can be made by means of resistors, which consist in general of single resistance units or groups of such units made of suitable material. These may be variable or fixed in value. Variable resistors are frequently called resistance boxes or rheostats, depending on their current carrying capacity and range. A resistance box consists of a group of coils of wire assembled compactly in a frame or box. It is so arranged that single coils or any desired combination of such coils may be introduced into the circuit by manipulating the switches or plugs. The extreme range of such a device may be from a hundredth or a tenth of an ohm up to 100,000 ohms. Each of its component units is accurately standardized and marked with its resistance value. By this means, it is possible to know precisely what resistance is introduced into the circuit by the resistance box. The coils are wound with relatively fine wire and in such a way that they do not have any appreciable magnetic fields about them. They are intended solely for carrying feeble currents, usually no more than a fraction of an ampere. Resistors of a single fixed value are convenient for many purposes. If they are carefully made and precisely measured, they are called standard resistance coils. Such standards may be secured in a range from 0.00001 ohm to 100,000 ohms, and of any desired current carrying capacity and degree of precision. Resistance boxes and precision resistors are designed primarily for use in the laboratory. The name rheostat is in general applied to a variable resistor having a fairly large current carrying capacity. A simple form of rheostat consists of a layer of German silver or nickel steel wire wound on an insulating tube with a sliding contact traveling along the tube so that the current may be made to pass through any desired length of the wire. Such rheostats are not usually made to handle large amounts of power. Larger rheostats are made of resistance units connected between the points of a switch as shown in Figure 15. The units are made of resistance wire embedded in vitreous enamel on a metal plate or wound on a porcelain tube and then enameled. For very large units, the resistors are made in the form of grids of cast iron, nickel steel, or similar metal, which are exposed to the air for cooling. The grid type of resistor is by far the most common in commercial use, especially for railway and electric crane control. For extremely large currents, a convenient compact rheostat is made by immersing metal plates to a variable depth in a conducting liquid. Such a liquid rheostat can be easily cooled by using a metal container or by changing the liquid as it becomes heated. Banks of an incandescent electric lamps in various arrangements are often used as resistors. The resistance of such lamps is subject to large variations in value with change in temperature. However, when operating under steady conditions, either hot or cold, they are satisfactory for many purposes. Such a rheostat offers the advantage of being readily adjustable by turning lamps on or off. It is compact and there is no danger of overheating. Another type of rheostat for handling large currents consists of a pile of carbon blocks or plates, which are compressed by a screw or lever to reduce their electrical resistance. Section 11. Conducting materials. Conducting materials, usually metals or metallic alloys, are utilized in electric circuits with two different purposes in view. In one case, a high degree of conductivity is required, while in the other case, relatively high resistivity is desired. These cases will be discussed in turn. A. If the conductor is transmitting energy to a distant point, by means of the electric current, it is seen from equation 2 that some energy will be wasted in the conductor in the form of heat. This loss should be kept as small as possible, and to this end, great care is taken in choosing the size and material of the conductor. For reasons of economy, the cross-section must not be too great, hence a desirable material. For conducting lines must have low resistivity and must be abundant and relatively cheap to produce. Such a material is copper, where lightness is important and where increased dimensions are not at disadvantage. Aluminum is much used. Steel is used where great strength is desired and where the current is small, as in telegraph lines. For lines which must stand great strain and at the same time be good conductors, such as radio antennas, a stranded phosphor bronze wire is often used. Section B. A material is to be used for resistor coils, on the other hand, should have the following properties. 1. Resistivity should be fairly high so that a large resistance may be obtained without too great a bulk. 2. The material should remain strong mechanically when heated. 3. The cost of material should not be excessive. For precision rheostats, for careful laboratory measurements, the following qualities, which are of comparatively small importance for ordinary electrical engineering work, should also be considered. Number 4. The temperature coefficient must be small so that heating does not change the resistance appreciability. 5. The resistivity must not change with time, even when the unit is heated for long periods. 6. The thermoelectric force between the chosen material and copper or brass must be small, so that the contacts between the different parts of the circuit will not cause troublesome thermoelectric currents. Iron is by far the most common material used in rheostats, since it is cheap, strong, and has a fairly high resistance. It is used in the form of grids for streetcar, locomotive, train, elevator, and crane control, and in the form of wire coils for handling smaller powers. German silver and the various nickel steels rank next in frequency of use and, with iron, make up the great bulk of commercial rheostats. Special alloys such as those called manganin and invar are used for laboratory units where the last three requirements mentioned above must be met. Table 21 of Circular 74 of the Bureau of Standards gives the properties of some pure metals and the composition and electrical properties of certain of the more common alloys. Wire gauges. Sizes of wires are specified in two general ways, either by giving the actual diameter in millimeters or in mils. 1 mil equals 0.001 inch, or by assigning to the wire its place in an arbitrary series of numbers called a wire gauge. Only two of these arbitrary wire gauges are of importance in American practice: the American wire gauge and the steel wire gauge. To avoid confusion, the name of the gauge must always be given with the gauge number. Most steel wire is specified in terms of the steel wire gauge. Wire used in electrical work, such as copper, aluminum, and the copper-nickel alloys, is specified in terms of the American wire gauge. This is the only gauge in which the successive sizes have a definite mathematical relation. It is convenient to remember that any change of the three sizes of this gauge doubles or halves the resistance of a wire. A change of 6 sizes doubles or halves the diameter, and therefore quadruples or divides by 4 the resistance of the wires. Section 12. Non-conducting or insulating materials. The importance of good conductors and practical applications of electricity has been dwelt on in the preceding section. It is, however, equally important to have non-conducting material in order that electric current may be confined to definite and limited paths. Such materials are commonly called insulators or dielectrics. It is a familiar fact that electric wires are covered with layers of cotton, silk, rubber, and other non-conducting compounds and are supported on porcelain knobs or in clay tubes. This is done to prevent the current from escaping along a chance side path before the desired terminal point is reached. Strictly, there is no such thing as a perfect non-conductor. The materials commonly used for this purpose have volume resistivities ranging from 10,000 ohms to 10 to the power of 17 ohms between opposite faces of the unit cube. This means that 1 volt impressed across such a unit cube by means of proper metal terminals would cause a current from 1 over 10,000 to 1 over 10 to the 17th ampere to flow. Most insulating substances show a decrease in volume resistivity with increase in temperature. These changes are irregular and sometimes rapid. They are not directly proportional to the changes in temperature. Humidity is of great influence and tends to lower the volume resistivity in such materials as slate, marble, hard fiber, and materials of phenolic type, such as material called bakelite. Phenolic is spelled Phenolic. Very frequently, surface leakage is of greater importance than volume conduction, and this surface leakage is largely dependent upon the conductivity of the moisture film upon the surface. In any event, care must be taken to ensure that the effects of surface leakage are either minimized or allowed for. In work involving high potential differences, the property of dielectric strength is of greater importance than volume resistivity. If the potential difference applied between opposite sides of a sheet of dielectric material exceeds a certain critical value, the dielectric will break down as though under a mechanical stress, and a spark will pass between the terminals. In case the dielectric is a liquid or a gas, its continuity is immediately restored after the spark has passed. However, in a solid dielectric, the path of the spark discharge is a permanent defect, and if enough energy is being supplied from the source, a continuous current will persist, which flows along the arc or bridge of vapor formed by the first spark. Dielectric strength is a property of the material which resists this tendency to break down. It is measured in terms of volts or kilovolts required to pierce a given thickness of the material and is sometimes called the puncture voltage. Values of dielectric strength of air are given in section 171, page 389. It is a quantity that cannot be specified or measured very precisely because the results vary with the character of the voltage, whether direct or alternating, the distance between the terminals, and the time for which the voltage is applied, and the shape of the terminals. The presence of moisture lowers the dielectric strength. Dry air is one of the best of the insulating substances, but its dielectric strength is lower than that of many liquids and solids. The dielectric strength of different specimens of the same insulating material is not directly proportional to the thickness of the specimen. The properties of the most electrical insulating materials are very different when subjected to radio frequency voltage than when subjected to the low frequency voltage such as is used on house lighting mains or when subjected to direct current. As an example, a piece of insulating material of the phenolic type may withstand 100,000 volts at a frequency of 60 cycles per second, but may deteriorate and become conductive very rapidly when subjected to a voltage or of the order of 20,000 volts or at radio frequency, say 120,000 cycles per second. In other words, some materials which are suitable for ordinary electrical work may be entirely unsuitable as radio insulators. Thus, slate is extensively used in ordinary electrical work with 60-cycle alternating currents, but is entirely unsuitable for use as an insulating material in radio frequency circuits. A certain amount of power is lost in every insulating material subjected to an alternating voltage, but the amount of power lost must ordinarily be small if an insulating material is to be satisfactory for most radio uses. Radio frequency power loss, therefore, becomes of particular importance in selecting insulating material for certain locations about a radio circuit. In addition to the constant currents which flow through or over insulating substances due to the body leakage and surface leakage, we find two other currents which are temporary when a direct voltage is applied, but which it is important not to overlook. 1. The displacement current, which is discussed later in section 29. This current appears and becomes negligible in a very short time, not more than a few thousandths of a second. 2. The absorption current, which persists longer and is observed when an EMF is applied to a plate of a dielectric by means of electrodes, as in the case of a condenser. At first there is a considerable rush of current, but the strength of the current falls off with the time, at first rapidly, then more slowly. It may not become negligible for several hours. It is due to some rearrangement of the molecules of the substance under the stress of the applied EMF. C. Potential difference, EMF, and Ohm's law. Section 13. The meaning of EMF. In Section 2, it was stated that one of the important electrical quantities in the electromotive force, which is the cause of the electric current, in order to fix in mind the ideas underlying the electric circuit, it will be helpful to consider some illustrations drawn from experiences familiar to everyone. Assume that a body of 1 pound weight is raised from the floor to a table through a height of 3 feet. Work is done upon the body, and the amount of work done is given by 1 by 3 equals 3 foot-pound. The body has acquired potential energy by this change in its position. That is, it is capable of falling back to the floor by itself, and in falling back it will, when brought to rest, do an amount of work exactly equal to that which was done in lifting it. The difference in level between floor and table may be expressed in either of two ways. First, in the ordinary way by stating directly the vertical distance through which the body was raised, and second, by stating the amount of work required to carry 1 pound of matter from the lower to the higher level. This difference in level then defines a very definite difference in condition between the two positions. The higher position, considered as a point in space, has a characteristic which distinguishes it from the lower position, and that is the amount of potential energy possessed by a body when placed there. In other words, a body placed at this point is able, by virtue of its position, to do a certain amount of work. If we assume that the body has unit mass, this characteristic is called the gravitational potential of the point. The higher position is said to have a higher potential than the lower position, and the difference in potential measured in terms of work is measured of the difference in height. Following this illustration a little further, we may consider the case of a simple pump, which raises water from a level S1 to some higher level S2. The water raised by the pump to the level S2 possesses potential energy, or energy of position. That is, it is able to fall back by itself to the lower level, and in falling back, it will do an amount of work exactly equal to that which was done in lifting it. Instead of measuring the difference in level by the height h, as before, it may be measured in terms of the work done in lifting 1 pound of water from S1 to S2. This difference in level may be called the difference in potential S1 and S2. The purpose of the pump is to transform the energy supplied by some steam engine or other prime mover into potential energy, with the corresponding difference in level or pressure head. This establishes what might be called a water motive force, which causes or tends to cause a flow of water through a return connecting pipe. Energy may exist in many different forms. The position energy or potential energy of a body has just been described. A moving body has energy of motion or kinetic energy. Sound, heat, light, and electricity are all forms of energy. These particular forms of energy are due to wave motion. Chemical reactions involve transformations of energy. Every action of everyday life involves a transformation of energy from one form into another. In the case of every transformation of energy from one form into others, it is found that the energy which disappears as one form can be entirely accounted for by the energy which appears in other forms. If the transformation is confined to one body or system of bodies, the total amount of energy possessed by that body or system of bodies is the same before and after the transformation. That is, energy can neither be created nor destroyed. This principle is usually referred to as the conservation of energy. It should be noted, however, that some forms of energy are far more available for use than others. Thus, the potential energy possessed by the water in a reservoir can be easily used, but the energy changed into heat by the friction of water with the sides of a pipe through which it is flowing is usually considered as being lost, because it is not practically available for use. Coming now to the electrical case, let us consider the electric current is supplied to the motors of an electric car by means of generator G and two conductors, the trolley wire and the track. Mechanical energy is being supplied to the generator by some source of power, such as a steam engine, and is being transformed into electrical energy. This transformation results in a flow of current as indicated by the arrows when a complete circuit is made through the car motors. This condition is described by saying that there is a difference of electric potential between the terminals of the generator, or between the trolley wire and the track. It is the purpose of any electric generator to set up this difference of potential between its terminals, which corresponds to the difference in the level of the water in earlier illustrations. Difference of electric potential is then a difference in electric condition, which determines the direction of flow of electricity from one point to another. Just as height of water column or a difference in level may be regarded as establishing a pressure or water motive force, which in turn causes a flow of water when the valves in the pipe are open, so the electric potential difference may be regarded as establishing an electric motive force which causes a flow of electricity when a conducting path is provided. Electric motive force may be defined as which causes or tends to cause an electric current. The unit of electromotive force is the volt. It is that EMF which will cause a current of 1 ampere to flow through a resistance of 1 ohm. The relation between electromotive force, current, resistance is called Ohm's law. This law is discussed further in the next section. The potential difference between 2 points may be measured in terms of the work done in conveying a unit quantity of electricity from one point to the other. In general, E equals W over Q, where E is in volts, W is in joules, and Q is in coulombs. In practice, however, it is measured by direct application of an instrument called a voltmeter. The unit of work or energy is the joule. It is the energy expended when a current of 1 ampere flows through a resistance of 1 ohm for 1 second. Power is the rate at which work is done. The unit of power is the watt, which is the power expended by a current of 1 ampere flowing through a resistance of 1 ohm. Power is sometimes measured in units of horsepower. 1 horsepower equals 746 watts. Section 14, Ohm's Law. If the pressure upon a pipeline is increased, the flow of water through it in gallons per minute is increased. Ohm found that an increase in the EMF applied to a given conductor caused a strictly proportional increase in the current. Doubling the EMF causes exactly twice as great a current as before. Trebling the EMF, 3 times as great a current, etc. This means that for a given conductor, the ratio of EMF to current is a constant, and this constant has been called the resistance of the conductor. This important relation is known as Ohm's law and may be written E over I equals R, or in the alternate forms, E equals Ri and I equals E over R. Ohm's law derives its great importance from the fact that it applies to each separate portion of an electric circuit and also to the circuit as a whole. Case 1. Ohm's law for a portion of a circuit. Assume some part of a complete circuit R, figure 19, which is held at a constant temperature and has no battery or other source of EMF. Between the points A and B, if current from an outside source is then caused to flow through R and correct instruments are used for measuring current and voltage respectively, the following data may be taken, showing that R has a value of 2 ohms and that R being constant, the current is directly proportional to the voltage. Suppose 2 straight lines, OY and OX, are drawn at right angles to each other. Divide each line into units and set down the proper numbers at regular intervals along these 2 lines. The numbers on the OY axis may be used to represent values of E, and the numbers on the OX axis to represent values of I. At a point 1 on the E axis, draw a light line parallel to the x-axis, and from the point 1/2 on the x-axis, draw a light line parallel to the y-axis. Where these two lines intersect, make a dot. Proceed in this way for all the corresponding values of e and I in the table above, and then connect the dots by a line. It is seen that the ratio of e to I is the same for every point that may be taken on the line OP. This means that e and I are connected by a constant factor, and I is said to be directly proportional to e. This process is called plotting the relation between the two quantities e and I. Proportionally is indicated by the straightness of the plotted line. Again, assume that a constant voltage E is applied across the terminals of R. By some suitable means, change the values of R through a considerable range. The following are some values which careful observation might yield. E volts, 24, R ohms, 2, I amperes, 12. Plot the values of R and I on a cross-section paper, and the curve A4 is obtained. Also, we may plot reciprocals of R, values of 1/R on the axis of abscissus against values of I on the axis of ordinates. It is now seen that I is proportional directly to the reciprocal of R, or in other words, I is inversely proportional to R. The student should make some experiments of this sort with a resistance box, battery, ammeter, and voltmeter. He should also make a careful record of the readings taken, and then should plot them on a cross-section paper as suggested above. From such a study, it will be found that A, for a constant resistance, the current flowing is directly proportional to the voltage. B, for a constant voltage, the current is inversely proportional to the resistance. It is customary to speak of the current flowing in a circuit, of the resistance of a circuit, and of the EMF between the terminals of or across any portion of a circuit. The relation expressed in equation 10 applied to a part of a circuit is used so much practically that the value of E between A and B has been given various names. It is called A, the RI drop, B, the potential drop, or C, the fall of potential in the portion of the circuit between A and B. If a branch circuit which contains a current indicating instrument, such as a voltmeter, is connected between these 2 points, a flow of current is shown to be taking place. The point A is at a higher electric potential than B, and hence current will flow along path A, B, V, B. Case 2, Ohm's law for a complete circuit. In extending this idea to the entire circuit, the total resistance of the circuit must be used. This must include the internal resistance of the generator or battery, or the sum of the resistances of all the generators, if there is more than one. Likewise, the voltage must be the resultant or algebraic sum of all the EMFs in the circuit. Ohm's law for the complete circuit may be then written in the form I equals E plus and minus E1 plus and minus E2 plus or minus E3 and so on over R1 plus R2 plus R3 plus and so on equals E over R. In this section, R must be the sum of all the resistances in the circuit, including the resistances of all the batteries or generators. In the same way, E must be the sum of all the EMFs, each with its proper sign. For example, there might be a number of cells or batteries in series, and one or more of these might be connected into the circuit with the poles reversed. These EMFs would have to be subtracted, hence the negative sign for the terms in the numerator. Another way of stating this general law when all parts of the circuit are in series is to equate the total EMF impressed on the circuit to the sum of the RI. drops in every separate portion of the current circuit. E equals Ri equals R1I plus R2I plus R3I plus and so on. Ohm's law is to be regarded as an experimental truth which has been established by countless tests for all metals and conducting liquids. For gases at low pressure, it does not hold nor does it apply to certain non-conductors such as insulating oils, rubber, and paraffin. 15. Sources of EMF. There are a number of ways in which electric energy can be derived from other forms of energy. Each one of these energy transformations sets up a condition which causes current to flow. That is, it produces an EMF. The principal sources of EMF will be discussed briefly in the following sections. Static or frictional electricity. When a piece of hard rubber is brought into close contact with a piece of cat's fur and then separated from it, two things may be noticed. 1. The bodies have both acquired new properties and are said to be electrified. 2. A force is required to separate the bodies and work is done if they are moved apart. Both bodies now have the power of attracting light bits of chaff or tissue paper. Rubber is said to have negative charge and the fur a positive charge. These charges exist in equal amounts and taken together they neutralize each other. An uncharged body is said to be neutral. When these charges are at rest upon conductors, they are called electrostatic charges. Electric charges may be communicated to small light bodies like pith balls. And if these are suspended from silk threads, the effects and properties of the charges may be studied in terms of the motions and behavior of the pith balls. Two pith balls charged oppositely are found to attract each other, and two with like charges to repel each other. The force between them in either case is proportional to the product of the charges and inversely proportional to the square of the distance between them. The force is also inversely proportional to the value of the dielectric constant of the material between the charges, if the charges and the distance between them remain constant. Electrostatic forces are ordinarily very small. There are many substances other than the two mentioned which become charged by friction with other materials. As glass is such a substance, the glass face of an instrument should never be wiped with a cloth just previous to use, as it thus may accidentally become charged to such an extent as to affect the light needle below it and cause a considerable error in its reading. In case this has happened, breathing upon the glass or wiping it with a moist cloth will remove the charge. If two conducting bodies carrying opposite charges are connected by a conductor, a momentary flow of current takes place and two bodies come to the same electrical condition. If the original charges were equal, both bodies are discharged. The flow of current continues for only a moment because there is no source of electricity such as a battery maintaining a constant difference of potential between the bodies. Electrostatic experiments can be best performed on a cold day when the air is dry. Batteries, when two plates of different substances such as two metals or a metal and a carbon are placed in a water solution of certain salts or acids, there is found to be a difference of potential between them. If the exposed parts of the plates called the electrodes are connected by a conductor, current will flow. The following list contains the names of some of the substances which are used as battery electrodes. The order of the arrangement is such that when any two are taken, current will flow through the wire to the one appearing higher in the list from the one farther down. In selecting materials to act as electrodes in batteries, the farther apart the metals are in this list, the greater is the electromotive force of the cell. The order shown is not absolutely invariable, but in some cases may depend on the electrolyte used. Zinc, cadmium, iron, nickel, lead, tin, copper, mercury, silver, platinum, carbon. The salt and acid solutions used are conductors of electricity, but their conductivity is not so high as that of the metals. They are called electrolytes. Some examples are solutions of sulfuric acid, copper sulfate, potassium chloride, and sodium chloride or common salt. Ordinary water from the service pipes contains enough dissolved substance so that it conducts electricity to a slight extent. With any two materials of the table dipped in one of the solutions mentioned, there will be produced an EMF and a resulting flow of current. The farther apart the selected materials stand in the list, the greater will be the effect produced. The arrangement for producing a current is called a voltaic cell. Several types of this cell will be described in sections 17 and 19. Thermoelectricity. Assume pieces of two different materials, Cj and the opposite Cj, soldered together at point J. The other end are connected by a copper wire through the galvanometer G. If the point of contact or junction J is heated to a temperature above that of C and the opposite C, there will be a flow of current through the galvanometer. This is commonly explained by saying that the junction J, heat energy, is transformed into electrical energy, and this junction is regarded as the seat of an EMF. In case the temperature of J is lower than that of C and C opposite, the direction of the current will be reversed. In the following table, some common metals are so arranged that when any two of them are chosen for the circuit, current flows across the heated junction from any one to one standing lower in the list. Bismuth, platinum, copper, lead, silver, and antimony. The presence at the junction of the intermediate metal or alloy like solder will not affect the value of the EMF developed, because whatever effect is developed at one point of contact with the solder is annulled at the other. Of the pure metals, the thermocouple made of bismuth and antimony gives the greatest thermoelectromotive force for the given difference in temperature. However, certain alloys are frequently used for one or both of the materials. The purity and physical state of these materials is an important factor in securing uniformity of results. A thermoelement or thermocouple may be calibrated with a given galvanometer. That is, a curve may be plotted coordinating microvolts and temperatures. It then becomes a valuable device for measuring temperatures, especially where other forms of thermometer cannot be used. For the range from liquid air temperatures, negative 190 degrees Celsius to 200 or 300 Celsius, copper advanced or iron advanced thermocouples are often used. For high temperatures upward of 1700 degrees Celsius, a thermocouple of platinum and platinum-rhodium alloy is used. Thermocouples find application in radio measurements and hot wire ammeters. See sections 59, page 136. Induced EMF. Electromotive force may be set up in a circuit by the expenditure of mechanical work in pushing wire conductors across magnetic lines of force. Also, when electric current in any circuit is caused to vary an EMF, which is the result of this variation, arises in any nearby circuit. The principles which apply to these cases are fully stated in sections 45 and 47, pages 108 and 112. The development of machinery based on these principles is subject of Chapter 2. The RI drop. When for some purpose a voltage is desired which is less than that of the available battery or generator, or one which can be readily adjusted to any desired value, it is often convenient to take advantage of the RI drop across a given resistance as described in section 14, and to arrange a circuit as in figure 24. The current from the battery which flows through the resistance AB can be adjusted to any desired value by properly choosing the values of AB. Since the voltage drop along AB is directly proportional to the resistance R, any desired fraction 1 over N times E opposite may be obtained by setting the contact C at such a point that the resistance AC is equal to 1 over N times R. This follows from equation 10, where it's seen that the EMF across any resistance is directly proportional to that resistance, so long as the current remains constant. This is nearly enough true for practical purposes if it be assumed that the resistance of AB is relatively large as compared to the internal resistance of the battery. The resistance AB may be in the form of a resistance box with a traveling contact at C, or it may be a uniform homogeneous wire with an adjustable contact point at C. Such a device for subdividing a voltage is called a voltage divider and has often been erroneously called a potentiometer. Standard of electromotive force. The EMFs due to the ordinary battery cells are usually between 1 and 2 volts. A certain type of cell has been selected by international agreement as standard of EMF. The type now most used is called the Weston standard cell because it was first suggested by Weston. It is also called the cadmium cell because cadmium is used as the negative electrode. This cell is made from carefully selected chemicals of great purity, and when used under controlled temperature conditions, its voltage can be depended upon to remain constant within a few parts in 100,000. At 20 degrees Celsius, its EMF is 1.0183. The value of the volts is maintained by a reference similar to cells kept in the National Standardizing Laboratories. 16. Internal voltage drop and line drop. Reference to equation, page 51, will show that the voltage or EMF of the generator, whether battery or dynamo, must always be thought of as expended in 3 parts as follows. 1. That part which sends current through the generator itself, called the internal drop. 2. That part which sends current through the line, called the line drop. 3. That part which sends current through the terminal apparatus, such as lamps, motors, or heating coils. This is the useful part of the EMF, the first 2 being wasted so far as useful work is concerned. This division of the generated EMF is illustrated in Figure 2.5. Since Part 3 is a part which is applied in the external circuit, it is clear that the generator must always supply a higher voltage than is needed at the terminals in order to take care of Parts 1 and 2. The above facts may be again stated in the form total EMF equals drop in generator plus drop in line plus useful drop in load. Voltage drop in battery or generator. Assume a circuit as shown in Figure 26. As long as the key K is open, the cell is not sending the current through the circuit R. A high resistance voltmeter V gives a reading E, which is the full open circuit voltage of the cell. The voltmeter current is so small that the cell may be regarded as supplying no current through it. If, without removing the voltmeter, the key K is closed, a current I flows through the external circuit R, and the voltmeter reading is seen to drop back to some value E opposite, which is less than E. As R is made smaller, the value of E opposite continues to decrease until when R equals 0. That is, when the poles of the cell are short-circuited. The voltmeter shows no deflection whatever. The rate of change of the current I is less than the rate of change of the external resistance R. The voltmeter indicates at any instant the then existing value of the voltage at the cell terminals, and this may vary from the open circuit voltage or EMF E to 0, depending upon the external circuit condition. For any value of R, the current flowing is given by the equation. I equals E divided by R plus capital R, where lowercase r is the internal resistance of the cell, or E equals Ri plus lowercase ri. Thus, the EMF E is equal to the sum of the potential drop in the cell and the RI drop in the external circuit. Denoting RI by E opposite, we may write the equation in the form E opposite equals E minus lowercase r times I. The quantity E opposite is called the terminal potential difference, or the terminal voltage of the cell, and it is always less than the full EMF by the RI drop in the cell itself. It may be defined as the useful part of the EMF, or that part which is available for sending current through the external circuit. The EMF E is determined once for all by the choice of materials used in the cell, and it cannot be in any way altered after the cell is chosen. The terminal voltage, however, can be varied through all possible values from E to 0. Anything that may be done to lessen the internal resistance of the battery, such as putting several cells in parallel, will lower the RI drop and correspondingly increase the terminal voltage E opposite. After the RI drop has been subtracted from the EMF E, the balance is the terminal voltage, or that part of the EMF which is available for work in the external circuit. The current drawn from the battery must be regarded as flowing through the entire circuit. As this value of I increases, the internal voltage drop in the battery increases, and a correspondingly smaller fraction of the total EMF is available for external circuit. What has been said here of a cell is equally true of any other form of generator. Voltage drop in the line. Suppose that a DC generator capable of supplying 118 volts at the outgoing wires of a powerhouse is furnishing current to a distant building for lighting lamps which require 110 volts. Suppose that the line resistance is 0.16 ohm and that the lamps require 50 amperes of current. There is then a line drop of 8 volts. And the available voltage at the generator is just right to operate the lamps at their rated voltage. Suppose, however, that other apparatus near the lamps, say the motor of an electric elevator, is put in operation, and that this requires 70 amperes of current. The line drop is then increased by 11.2 volts, or 19.2 volts in all, and the voltage available at the distant end of the line has fallen to 98.8 volts. This is not enough to maintain the lamps at full brightness, and they are dimmed perceptibly every time the elevator is operated. To correct this difficulty, a new line of lower resistance must replace the old one. That is, the line drop must be decreased so that for the maximum current demand the lamps will not fall below 110 volts. Another example of the line drop is seen in the dimming of the lights of the trolley car when the car is starting. The resistance of the trolley car is kept low by using a large cross section of copper, and the track resistance is kept as low as possible by careful bonding at the rail joints. However, a few defective joints raise the track resistance and increase the line drop to such a degree that the necessary lamp voltage cannot be maintained when the car starts.